Hello dear students, how are you? Today we will start in series of applications of Gauss's theorem. The next topic is electric field due to a charged thin spherical cell. So first of all, we will discuss what is thin spherical cell. Thin spherical cell means a sphere having inner and outer radius approximately same. It means we have its diagram like this. Its inner and outer radius will be approximately same. This is spherical cell. Now we are taking a spherical cell of radius capital R. By application of Gauss's theorem, we have to determine its electric field. So look here, we have to determine electric field due to cell at three different positions. First one is what? First one is a point outside the spherical cell. Second point is at the surface of a spherical cell. And the third point is inside the spherical cell. So look here, we will start. Let a charge Q is distributed over the surface of a spherical cell of radius r. All of you know, since charge is distributed over the surface, so we have to use surface charge density. So since surface charge density, sigma equals charge per unit area. So we can write the value of K 4 pi r square into sigma. So the value of Q is what? 4 pi r square into sigma. Now we have to determine magnetic field at point P. So first case, remember dear, we have to determine electric field at three different positions due to a thin spherical cell. First one is at a point outside the spherical cell. We can also write in symbol small r is greater than capital R. It means the distance of point P from the center is smaller. Now look here. If we want to calculate the electric field at point P, then we have to draw a Gaussian surface. So look here, the spherical surface has spherical Gaussian surface. Now we are taking a small surface ds and the direction of electric field at this point, vector. Let d phi be the small flux through the small surface, ds. d phi equals vector E dot ds. So we can write E dot ds cos theta, and if we look, the direction of electric field and the direction of vector area both are same. So we can write theta equals 0 degree, and we know cos 0 is 1. So the value of d phi is E into ds. For total flux, phi, we integrate d phi over the limit of surface area, surface integral of E dot ds, and when we integrate it, integration of ds will give you, how we integrate ds, please look here. If we integrate ds, it will give you surface area, and the surface area of sphere is 4 pi r square. So we are getting 4 pi r square. According to Gauss's theorem, since phi equals q upon epsilon naught, so we can write q upon epsilon naught equals E into 4 pi r square. Now we will get E equals 1 upon 4 pi epsilon naught q upon r square. Look there, it is the value of electric field at point P in term of Q. We have the value of Q. Please remember, in some questions surface charge density is given, so you can replace Q as 4 pi r square sigma. So you can write it E equals 1 upon 4 pi epsilon naught 4 pi r square sigma upon small r square. 4 pi cancel. E equals sigma upon epsilon naught capital R square upon small r square. It is your final result. The electric field due to spherical cell, thin spherical cell at point P. Now we have to go on case number 2. What is the meaning of case number 2? Because if we take a different position of P, it means we can take point P at the surface of spherical cell. Now in second case, I am taking the point P at the surface of sphere. So look here, what will happen? If I am taking the point, it is case number 1, please remember. I am trying to calculate, or we are calculating the electric field at the surface of thin spherical cell. It can also be written as small r becomes equal to capital R. Now look here, it is very simple. Since electric field What is the electric field you got at point P? E equals sigma upon epsilon naught capital R square upon small r square. Small r square. Since small r is equal to capital R, so electric field E equals sigma upon epsilon naught capital R square upon R square, and you will get electric field E as sigma upon epsilon naught. Now dear, it is the case when electric field, when we calculate electric field due to thin spherical shell at its surface. Now the last case number 3. Point lies inside the spherical cell. Look here, we are talking about electric field inside the thin spherical cell. So we have to write, since the charge lies on the outer surface of thin spherical shell, so inside electric field, R is less than capital R, A becomes equal to 0. And remember dear, electric field inside a conductor is always 0. The electric field inside the conductor is always 0. Now, on the basis of these 3 cases, we will draw a graph. So, our next and last point of this derivation or this concept is to draw the graph between electric field and distance. Electric field versus graph between electric field and distance R. And you can say electric field versus distance. So look here, how we draw the graph. We are taking electric field on y-axis and we are taking distance on x-axis. Origin, this distance is r. R means radius of spherical cell. Always remember, dear students, please remember this graph is very important. Always remember, inside the spherical cell electric field is 0, and outside the spherical cell electric field decreases as a function of R. It means you can say since E is inversely proportional to R square, so you can draw a graph like this. This graph shows electric field is inversely proportional to R square. Remember dear, this case is very important and you have to take three concepts in your mind. One, you have to determine electric field at point P, which lies at outside. P lies outside the spherical cell. Second one, P lies at the surface of the spherical cell. And the third one, the point P lies inside the spherical cell. And this graph.